Okay, so in the last class, we said that we need to discretize del phi del t in del phi del x I or del phi del x ij or del 2 phi del x I. So these terms need to be like that. These terms need to be discretized. Okay. So how do we do that? So that is our the main job. So let us consider a derivative of, let us consider del phi del x I. Okay. So if you simply see this, del phi by del x is nothing but d phi by dx, and d phi by dx is nothing but a slope. Okay. So if we have a x point here, and if we have a x plus delta x point here, okay, and there is a curve, for example, then a tangent at this point will have a some slope, and that slope will be the value of the phi. Suppose we are dealing with a phi at x plus delta x, and this is a phi x. Okay, and if x and x plus delta x, from this definition, they are separated by distance delta x. So the slope, this is a slope. The slope can be represented as, so we know that d phi by dt or d phi by dx is equals to limit delta x tends to 0, then which if delta x tending to 0, it becomes a derivative at that point x. So the derivative of phi with x is represented as phi x plus delta x minus phi x delta x. This is not a one and the only one unique. We can also represent, rather than taking x point, we could have taken x minus delta x point, and we could have got the slope. Okay, we could have got the slope by taking x minus delta x point. Okay, so we can write this again as, say now I'm writing del phi by del x is equals to limit delta x tends to 0, which also can be written as phi x minus phi x minus delta x divided by delta x. There is another possibility is also there. Rather than considering the x and x minus delta x or x and x plus delta x, we can consider x minus delta x and x plus delta x point, and also we can represent a derivative del x is equals to limit delta x tends to 0, and we could have written phi x plus delta x minus phi x minus delta x, and the distance separating these 2 points. Distance separating this is twice delta x. So 2 delta x. So these 3 definitions are available for us, and now for in our case, how we can represent them? How we can represent them for our case? Our case is del phi by del x at ith point. Okay, at ith point we can write it as simply the same thing. We can simply remove the, we can make a finite divided differences rather than derivatives. We'll avoid this limit and simply write x plus delta x minus phi x divided by delta x, and here del phi by del x at I phi x minus phi x minus delta x divided by delta x, and this third case simply we are representing phi x plus delta x minus phi x minus delta x divided by twice delta x. This also can be represented. Suppose we have del phi del x ij. Okay, then it can be represented as phi x, but we are taking del x. So x plus delta x comma y minus phi x comma y. Y is not changing. Y is not changing. Y is not changing. Since we are taking derivative of phi with respect to x, it can be represented like that. Suppose the same thing you have to write in ijk del phi del x in ijk. This would have been phi x plus delta x y comma z minus phi x comma y comma g comma t. Sorry, t will come when we talk about third part divided by delta x. There can be other representation possible also, which can be combination of any other I also. It can be combination of I, n, j, ijn or ijkn. This can be represented by x plus delta x comma y comma z comma t minus phi x comma y comma z comma t divided by delta x. Similarly, you can write these differences also. Okay. Similarly, you can write these differences. The first one you have seen, this representation of or any other representation is called as forward difference. Okay. So I'll just write simply again here. Del phi by del x I, which can now be written as x plus delta x can be written as I plus 1. Since we are, suppose we are talking about one dimensional and this is a x and this is x plus delta x. We represent this x plus delta x by index notations. So x is represented by I, x plus delta x represented by I plus 1, and x minus delta x is represented by I minus 1. Okay. If y coordinate is also involved, then you will have to bring j index here, and if the g coordinate is also there, then you have to bring in k coordinate also here. Okay, if you understand for one dimensional, you should be in a position to extend for 2D or 3D. So I simply write phi I plus 1, this thing I am simply writing here, I plus 1 minus phi I divided by delta x. If it is ij, then you will have to, if it is ij, then you will have to write I plus 1 comma j, I comma j. This is called as forward difference, forward difference formula, forward difference, forward divided difference. Okay, this is also difference, this is also difference, and this is a forward difference. So forward divided difference. It's not simply a difference. Okay, next del phi del x, next representation, say again we are talking about ij for example, then phi ij I comma j minus phi I minus 1 comma j divided by delta x. This is called as backward divided difference. And the third one, del phi by del x ij is equals to phi I plus 1 comma j minus phi ij divided by twice, excuse me, I minus 1 comma j twice delta x. This is called as central divided difference. So such things are there. Now for one derivative, we have three options. Number one, this option is available, this option is available, and this option available. Now the question is, which difference divided difference equation, which divided difference equation, actually there is a hyphen, they are connected. Which divided difference is good? Okay, the answer is it depends upon, it depends on the order of accuracy. It depends upon the order of accuracy, order of accuracy. This is a new term. Order of accuracy of the divided difference equation, of the divided difference equation. Okay, so now our objective should be to find out what is the order of accuracy of these schemes. So our objective is to estimation of order of accuracy of forward difference scheme. Forward difference. We call these as schemes. Forward difference, simply written as FD schemes. Scheme. Okay. So to estimate the order of accuracy of forward divided difference, and what was the forward divided difference for del phi by del x? I, our forward difference was I plus 1 minus phi I, phi x, sorry, phi I divided by delta x. So we were essentially talking about this ith point and I plus 1, which is having a distance delta x, and all other points also at same distance, so uniform grading. So we take a help of a Taylor series. Okay. We consider because we have in del phi by del x, we have terms like phi I plus 1. We have a phi value of the variable at I plus 1. Phi is a variable, I plus 1 is its index. So phi at I plus 1 and phi at I are involved. So how I can get an expression for phi I plus 1? So we consider a Taylor series to obtain the values of to obtain the values of phi at phi I plus 1, or we simply say the value at I plus 1, that is phi I plus 1. This value has to be I plus 1. We, to obtain the phi plus 1 around I. If it is ij, then we will say phi at I plus 1 comma j, that is phi I plus 1 j around ij. Okay. So what is the Taylor series formula for calculating a phi I j around this I? Okay. Around this I at I plus 1, what is the variation of phi? What is my phi here? What is my phi? That variation of phi from I to I plus 1 point can be given by Taylor series expansion. Or simply Taylor series. Okay. That phi I plus 1 is equals to value of the phi at I plus the derivative of phi, first derivative of phi with respect to x. Now we are talking about x, so since we are talking about x coordinate, del phi del x I multiplied by the distance delta x plus the second order term del 2 phi by del x I, and delta x into delta x divided by 2 factorial plus now by similarity you can assume that we have other terms like del 3 phi del x3 I plus del x 4 factorial del 4 phi del x 4 plus so many terms. Now here we see phi I plus 1 is a phi I means the constant value. You can say that my phi I is nothing but simply suppose phi I is 1. Suppose phi I is 1, then you can say that either my phi I plus 1 can be a 1. Means it is simply a constant assumption. Suppose this is a phi value, then at I and I plus 1, we are saying that it is simply a constant value. But suppose you add a second term, delta x delta phi, then it is a first order curvature. So it can be either a first order curvature is added. Okay. Need not be necessary that always the function is constant. It can be of any type. Also, it can have a second order curvature. Okay. It can have third order curvature. So more and more you add number of points, number of this geometrical parameters, you get a better representation between I and I plus 1. Okay. So any function can be any functional value at new point can be represented with previous point with this additional terms. That is a Taylor series. So from this Taylor series, you can also see now that you can see similar kind of terms. So try to bring them together minus phi I, and also you bring this delta x here. You divide phi I plus 1 minus phi I divided by delta x. So you get this delta x now get cancelled. So only you get del phi del x I plus now you get delta x square divided by delta x 2 factorial del 2 phi del x 2 plus del x 2 3 factorial del 3 phi del x 3 I and many other terms. Now what do you see? Comparing these two equations, you see that del phi by del x at ith point is nothing but equals to phi I plus 1 minus phi I excuse me divided by delta x with additional terms. It's not exactly this term. Okay, if you compare these two, you see that it is up to this, but you have additional terms here. So these additional terms are called as truncation error. This formula is a truncated formula of this del 2 phi del x2 plus or minus del x2 3 factorial, and likewise leave these terms. So here this term, second term, which we now see is called as truncation error. This is called as truncation error. T dot E dot. Okay. Now here the first term which is having a lower power, lowest power term. The lowest power term of step size, this is delta x is a step size, or you can say grid size. Okay. These derivatives can always be represented in terms of this delta x. So first term, which is having a least power, any term, need not necessarily be always it is delta x. It can be delta x square if it is delta x is not there. So first term, which is having a lowest order among the terms in truncation error part, that is called as leading error term. In this truncation error, this is called a leading error term. Why it is called a leading error term? Suppose there is a error in x, delta x. That error is suppose or value of the delta x is 0.1, and you take the delta x square, this value will be smaller than this value, isn't it? So always the highest value will be the least order value, the value for which a power is the lowest power. That value will be the dominant one. So that is the reason we call it as a leading error term, because it gives more error compared to other terms which may become negligible. So leading error term is main. And now we say that this del phi by del x representation, del phi by del x I with this forward difference phi I plus 1 minus phi I divided by delta x is of order delta x, okay, plus order delta x. We do not say all the terms, we just keep the leading error term and say that this whole truncation error is of order delta x. So what do you mean by delta x? This truncation error is of order delta x. Okay. Since the order truncation error is of order delta x, we say that the order of accuracy of this forward difference, the order of accuracy of forward difference scheme is delta x. Okay. So only first order. So we say that that is first order accuracy. First order accuracy. It is called as first order accuracy, or rather than accuracy, accurate, first order accurate. For this particular statement. Okay. Now similarly, if you perform backward difference also, okay, similarly, if you perform backward similar argument, similarly for similarly the order of accuracy, the order of accuracy of backward difference BD is delta x. That is, it is again a first order accurate. That is first order accurate. What about central difference? So estimation of order of accuracy of central difference CD. So to do that, what is the central difference expression? First look at that. Del phi by del x at I is phi I plus 1 minus phi I minus 1 divided by delta x. So in this case, what we have to do is we have I point.
That divided by 2 delta x.
Yes. So here we have I point I plus 1 and I minus 1. So we'll take a Taylor series around I and evaluate phi I plus 1. Okay. And we'll take another Taylor series for I minus 1 to calculate phi I minus 1 around I. Okay, so first is already there, but again I will write phi I plus 1 will be equals to phi I plus delta x del phi by del x plus delta x square 2 factorial del 2 phi del x2 plus delta x 3 factorial del 3 phi del x3 plus other terms. Phi I minus 1, you have to be little careful. In this case, phi I is a positive, then first term, second term coefficient should be negative because it is in negative direction from the I. So minus delta x del phi by del x I. And second will be a positive because delta x square, negative delta x square will become positive. So delta x square 2 factorial del 2 phi del x2 I. And here again it's a negative square and then multiplication by the positive negative. So delta x cube 3 factorial del 3 phi del x3 plus other terms plus minus here. So you see minus plus then minus plus will keep on coming. Now from this you substitute here. So from that you can say that del not substitution, you have to say like this phi I plus 1 add or subtract equation 1 and 2, subtract equation 1 and 2. So phi I minus 1 is equals to phi I will go out. This minus minus will become plus twice delta plus delta x minus of minus delta x twice delta x del phi by del x, and here plus minus it will go out, and here we'll get plus twice delta x cube 3 factorial del 3 phi del x3 plus. Now you divide this by delta x twice delta x, divide by twice delta x. So we get phi I plus 1 minus phi I minus 1 divided by twice delta x is equals to del phi del x I. These are all at ith point, huh? Plus, so twice delta x gone there, so we have delta x square 3 factorial del 3 phi del x 3 I and other terms are also there. Now, what do you see here? From this, we again see that del phi by del phi by del x I, which is our required derivative, and this is our finite difference, okay, finite divided difference. It is a central difference, but finite divided, not forward. Minus phi I minus 1 divided by twice delta x is having this leading error term. Okay, this is our truncation error, isn't it? This is our truncation error, and this is our leading error term. And leading error term is of order delta x square. Okay, so this is, we say that leading leading error term is of order of leading truncation error is of order of truncation error is of is order of delta x square. Okay, so what do you say that the central difference? This means that the central difference CD scheme is second order accurate. Second order accurate. Okay, so which one is better? So in the forward difference, you get delta x, order of delta x, and in this backward difference, again you get order of delta x accuracy, and in central difference you get order of delta x square. Okay, so error is order of delta x. So suppose delta x is 0.1, so here also it will be 0.1, and this will be smaller than 0.1, less than 0.1. So any value if you take of delta x, in central difference the error will be always, which implies that error will be comparatively comparatively smaller in CD as compared to forward difference or backward difference. Okay, so the most accurate is the most accurate among three, the most accurate discretization of del phi by del x at I is given by the central difference. central difference scheme. Okay. So central difference scheme gives us a best results. Now, how we can do for say, excuse me, say we have a time derivative. How will do for time derivatives? Say we have a time derivative. Suppose we have a del phi by del t I. So here I will have a role in the sense that t has to be connected to space. Okay. So which time, which space you are talking, so that we have to be considered. So n will be represented by time and I will be space. So here we will have to say that I'm talking about ith point. Now there is no x derivative. So you write only phi I minus phi I. Okay. But you do a difference in terms of time. Now here we are saying that this is my ith point, but this is n and I want to move in n plus 1. This is your time axis now. Okay. And this n plus 1 and n are separated by distance delta t. So we say that n plus 1 n is a forward difference expression for delta t, delta phi by delta t. You got it? So similarly, you can write a backward difference for it, but uh, you can write like that: del phi del t I n is equals to phi I n minus phi I n minus 1. You can have minus 1 also, since you have n and n plus 1, you should have a decrement also n minus 1 like that. And this is I, ith point. So you say delta t. Similarly, we can talk about these two n plus 1 and n minus 1 points, these 2 points, and take a difference del phi by del t I at n can be represented by phi I again, phi I n plus 1 n plus 1 minus n minus 1 divided by delta t. Now, what will be the order of accuracy of this scheme? The order of accuracy of this scheme will be again delta t instead of delta x. Order of accuracy of this will be delta t, and order of accuracy of this will be order delta t square. Okay. How? How is it? You have to do the same Taylor expansion of phi I n plus 1. Okay. Taylor series expansion expansion of phi I plus 1 around phi I n. So what is the value over here of phi? This is phi I n. Here the value is phi I n plus 1. Here the value is phi I n minus 1. So around phi, you have to do the Taylor series expansion. So that Taylor series expansion looks like this. Phi I n plus 1 is equals to phi I n
Actually, sir,
plus uh,
sir, in the means sir, third line, sir, del phi by del
uh,
t ni, sir, in
uh,
the denominator b should have
twice
two, yes, sir, two del dot. Yes, sir, thank you, sir.
del phi by del t at I and n plus delta t square 2 factorial del 2 phi by del t to I n plus likewise. Okay, so let me write third because this is coming, this is playing a role. So 3 factorial del 3 phi del t 3 I n and likewise. Phi I n minus 1. So we say that phi I n minus delta t del phi by del t I n plus delta t square 2 factorial del 2 phi del t square I n minus del t 3 factorial del 3 phi del t3 I n plus. So again, same thing, isn't it? So you can subtract second equation from the first equation. The subtraction will give you phi I n minus 1. And if you divide it by the the twice delta t, you will get this delta t square divided by 3 factorial along with this term del phi by del t I n plus del 3 phi del 3 I and n. So you see that del phi by del t that I and n is equals to nothing but phi I n plus 1 minus phi I n minus 1 divided by twice delta t minus delta t square 3 factorial del 3 phi del t3 okay I n, and you will get another term. So first leading error term again is, so we say that it is like this. Or you can say plus also, it depends upon what is x dot t like that. So delta t square. So this expression, central difference equation for time, is a second order accurate description of in the time discretization. Second order accurate in time. Okay. So we say now here a time word has come now. There you can say space, second order accurate in space. Second order accurate, now we will say here the CD scheme for del phi by del t in is second order accurate in time. Okay. Similarly, you should be in a position to do this analysis, truncation error analysis for any other scheme. Okay. So we see that from this, we see that whenever we try to get a discrete form of these derivative terms, say for del phi del x I or j, this thing, we always get a discrete version. Okay. We get some discrete version plus error. Okay. So we get some difference. This is difference equation, difference equation and plus error. This error is a dangerous thing. That is the reason we say that del phi by del x is approximate. If error is minimum, if this is error neglects to 0, then this representation del phi by del x I is exact representation by this bracketed term without error. But with error, we have some approximate no value of del phi by del x. So the job is to reduce this error. Okay, always. So we would like to have a scheme which will have a higher order of accuracy. Okay. So we always would like to have error tending to 0. Okay. Therefore, we should look for the higher order accurate schemes. Just give me a second. Therefore, we should look for higher order accurate schemes in time and space. Okay. So minimization of error, and we know that there are two types of errors. Errors are of two types. Now what we are seeing, there are two types of error. What we are seeing now, this is the truncation error. And this is controllable, isn't it? By changing the order, or making delta x very, very small. So playing delta x, making delta x tending to 0, you can minimize, we can minimize error. But there is another error which is called as round off error. Round off error. It is inherent in computation. Okay. So inherent in computation. Inherent in all computations. We already seen in your first previous lectures that computer stores only finite number of digits. So it chop off or round off the value. So this rounding off, once we do multiplication, division and all the mathematical operations, these round off errors keep on growing. Okay. So that is beyond your control because all systems are finite systems. So there is a possibility of having round of error, but maybe minimized. Truncation error is somewhat in our control. Okay. So how do we control truncation error? Already I have said that we can, minimize the uh, truncation error is depends upon the delta x.
Hello, sir.
Sir, we
Class
have
time is
class.
over.
Yes,
Okay.
sir, we have next class.
Okay, so we stop here.